Hello there, this is Toby. With this video, I want to show off some work that I've done during the holidays. My family went on a vacation, and for some of the days, due to the jet lag, I got up very early in the morning and did some coding. And I want to show you the stuff that I've been working on. That coding, I did that up until the point I got sick, and then I stopped doing that. But anyway, I think I did some really exciting stuff, so that's what I want to share with you. I'm not going to share the rest of my holidays with you. If you want to know more about that, you're gonna have to ask me in person. Okay, so what have I been working on during my holidays? I had up till that point, I had been thinking a long time about a concept, and a concept called the time travel debugger. Time traveling debugger, if you will. So the time traveling debugger is a debugger that can go back in time, essentially, where if you have lines of code, a normal debugger, will be able to sort of step through line by line, here, and then here, and then here, and so forth. A time traveling debugger is able to walk backwards in time. So that's what a time traveling debugger is. And I thought of a scheme of how this could be implemented, and and I did it. At least I did a sort of very early prototype version of this as a proof of concept that this is actually possible. So let me show that to you. I used the Funlang programming language to implement this idea on, because I made this Funlang recently, and it's a very simple and small programming language, so that was very good for my purposes of trying this out. Okay, so let me show you how that works. So I have in this play directory within this Funlang language, I have a few programs written in Fun, and so this is a Hello World program written in Fun, and in Fun, the entry point of every program is a main proc, and in Fun we have procs and funs. So like this is a fun, and funs are supposed to be pure functions, whereas procs can be impure, if you will. So that was the main idea of the Fun programming language. But anyway, so let's say you wanted to run this program. What you would do is go to the command line and say node scripts run.js, and then you give it the file path of your program, and it runs your program. So simple. Notice that after you run your program, that history file has been generated, and I'll talk more about what that is after I show you this example. So this example is a while loop. It just counts from 1 to 10. Let's run that guy. So there it is. It'll count from 1 to 10, and then at the end it says done. And again, it creates this .history file. What this .history file does is it enables the time traveling debugger. So let's use the time traveling debugger. So you do node and then scripts /debugger, and then again the path to your program, like that. and the debugger will sort of read in the source code, and it'll also read in the .history file. And what it does with the .history file is actually the .history file has a snapshot of the entire state of the program at every step of the program, which is what allows the debugger to go back and forth like a VCR, essentially. So at the beginning, we're at line 1 of this program, or I should say line 2. We execute that. The next step, we can see that on the stack over here. That's the middle column. So this guy is the stack. Incidentally, this guy is the heap, which I'm gonna show that off later. Currently, we don't have any objects in the heap because only arrays and dictionaries are stored in the heap, and this program doesn't have either of those things. Okay, so but I guess what the stack shows is the stack has a number of frames, which I should probably show that, but currently there's only one frame. The frame for this main function. So this is the main. I'll call this the main frame, perhaps. Although the word mainframe is kind of overloaded. So the mainframe currently has one variable in it, count, and its variable is 1. And the value is going to change as we step through this function. So every time I update the value of count, you can see the value of the variable update within the frame. But because this is a time-traveling debugger, I can step backwards in time. And I'm just using the up and down arrow keys to step forward and backward. So I can either step forward or backward, and it'll sort of display the state of the program at that point in time. And now we're at the end of the program. So that's the idea of the time-traveling debugger. I'll show you another example. I'll show you a couple more examples before I actually explain how it works internally. I have a Fib program which calculates a Fibonacci number, or it goes through a Fibonacci sequence. I have two versions of Fib actually, the Fib with a while loop and the Fib with recursion. Let's just see both of those because we are computer science geeks. We are very interested in the Fibonacci sequence. Okay, so it calculates the Fib of 5 is 5. Doesn't seem very interesting. Let's go Fib of 8. Fib of 8 is 21. So now let's use the debugger to sort of examine what happened. Okay, so at the beginning, we're going to we're at here where we call the Fib function, and when we sort of move to the next line, it finds itself in the top of the Fib function, which makes sense. And here is where the stack frame gets another frame. So this is, and again, the center column here, this is the stack frame. And currently we have the main frame, which again, I hesitate to use that word, the main frame, but I just did. But now we have a Fib frame. Fib frame. And a Fib frame, a new frame is created whenever a function call has been issued. And so this records the parameter that went in to that function. And then within the frame, we have the current state of the local variables of the function. So now you can see the multiple frames in action. And now the first thing the Fib function is going to do is instantiate an I to 1. It'll also make two more variables, this Fib I and Fib II. Fib I in this program used to mean the current Fibonacci number, whereas fib_ii is used to represent the next Fibonacci number after the current one. So fib_i is fib of 0 at present, at least it's supposed to be, and fib_ii is supposed to be fib of 1. So it loops through, and we have used this temporary variable to do this swap thing, because to generate the next Fibonacci number after that, that should be the sum of fib_i and fib_ii. So temp would have been fib_ii, but then we do this swapping thing so that fib_i ends up being the value of fib_ii, and fib_ii ends up being temp, which would have been fib_ii. And we basically do this thing over and over again. And you can see the values change as we step through the code. And a normal debugger can do this. The time traveling debugger can also work backwards in time. Okay, so we're gonna step to the end of this program, and at the end of the program it shows you the return value when it encounters a return statement. And in this case the return value is 21. And now it shows the result as 21, and it shall print that result. Okay, so let's do the same thing with the recursive version of Fibonacci. So we're gonna run fib recursive.fun. Let's get it to go. No, I'm just gonna go with a small number, because otherwise the stack frame gets a little bit long. So now I'm gonna use the debugger on fib recursive. And fib recursive works recursively, as the name implies. So if you call fib5, it's actually gonna call fib again for fib4 and fib3. So let's step through it to actually see that rather than me telling you. So okay, so we called fib5, and you can see the n parameter to fib was 5 in this instance of the call to fib. And this conditional doesn't hit, so it skips this if statement, and it will skip this n equals 1 conditional as well, and it lands us here. And then this is gonna make another call to fib with n minus 1. So that's how we got fib n equals 4 here on top of fib n equals 5. Now we have more stacks. We have 3 stacks at this point in the stack frame. And again, n is neither 0 or 1, so we have to make yet another fib call, this time with n equals 3. And that happens again for n equals 2. And it happens once more with n equals 1, but this time, because n equals 1 is going to return 1. And when it returns 1 here, we're still in the n equals 1 version of fib. Once we return it, we pop this stack. Means this guy will get destroyed because we returned from it. We terminated the execution of this function, and we'll come back to this frame after. So there we go. So now we come back to this frame where n is equal to 2. And because this function call just returned with a value, and we step through this, fib of 1, or fib1 is going to receive the value that this function returned, which was 1. And if you don't believe, we can just step backwards a couple of steps to see that the return value was 1. So that's how we got the 1 in fib1 here. And then the next line makes yet another call to fib. So, and this time we want to get the fib of n minus 2, because n is 2, n minus 2 is 0. So this call is going to be n fib of 0, which, because that's 0, it shall only return 0. And we can see the return value is 0 now, and we pop that stack off, and now we're back to the frame for fib n equals 2. And yeah, and this fib underscore 2 is going to return receive the return value of that, which if we walk back by 1, we can see that should be 0, and therefore now fib2 has 0 in it. And now we're going to return the sum of fib1 and fib2, which is 1, and 0, which was 1, and this 1 is going to come back to the fib(n) equals 3 frame here, and so the return value goes into here and gets stored into fib_1 of this frame, and so forth and so forth. So if we step through this entire program, I'm gonna go faster. At the end, when are we gonna get to the end? This is quite a long-running program. Oh, I think we are about at the end now. Yeah, we are. The return value of fib5 ended up being 5 because this would have been fib3. Fib3 is 3, and fib4 is 3, and fib3 would have been 2, and the sum of those is 5. And then we're gonna print that out. Okay. All right, so that's basically a run through of how this debugger works. One thing to note about the debugger is that the debugger never needs to re-execute this program in order to work, because the debugger works entirely off of the history file, which essentially contains the snapshot of every single state within the program. So how does this work? So let's go in and look at one of these history files. Let's actually start with a simpler one. Let's start with this while loop one. Okay. So this history file is in sort of JSON format, but it's a JSON format with an extension that I added, and I called it JSON R, which stands for JSON with refs. What is refs? A ref is an ability for one section of the JSON file to reference another object or array within the file. So there's two syntaxes that JSON R introduces in addition to JSON. One syntax is this and then a number symbol, and symbol and then a number. And this is saying I'm defining, the number, by the way, is an ID for this particular object that follows. So we're saying this object here, this whole object here, we're gonna give it an ID of 1. And when you use this and symbol, you're saying I'm defining the ID 1 as this object. And here, the same thing. And 2 means we're defining the ID 2 to be this object that comes right after this ID definition. When you see a star and an ID, that it's a reference. That means like the value of spouse should be referencing the object that was defined as ID 1. So this should point to this whole thing, essentially. Okay, and that's how that works. So the reason I decided to implement this is because I wanted to make use of structural sharing to reduce the file size of the history file. And I'll show you how that comes into play. And also that's an area where there's still work to be done to really optimize the file size, because currently it's definitely not optimal yet. But anyway, so you can think of this as basically a JSON format, more or less, with the addition of this ref thing. And in a history file, it's got a number of entries. It's an array, right? The top level object of the history file is an array, and each item in the array is a snapshot, basically. So this object is a snapshot, this object is a snapshot, etc. And what is in a snapshot? A snapshot has a line number, so that corresponds to the line within the source code. So in other words, this guy here, it's a snapshot taken at line 2, and this guy is the stack, the state of the stack at that point. State of stack. It's the state of the stack at that point, and as I should say of the stack frame. And the stack frame can have any number of stacks, and this one just has one. So this guy here, this is the only frame. In fact, it's the main frame of the stack, and it tells you the parameters that it has the function name, the function call that initiated this stack, and it has the parameters that were passed in. But this guy is definitely, the parameters there are no parameters, so this is an empty object. So this is an empty object, and this and1 just defines the empty object as the ID 1, and variables is pointing to the same empty object, so there's no variables at present either. So I mean, that's an example of structural sharing. It's just sharing a very small object, so it's not buying you very much in this case, but it is there. When the objects become larger, then structural sharing saves much more space. Okay, so this is basically the first snapshot, and then there's the second snapshot and the third snapshot, and so forth. And we can sort of follow the chain of events just by looking at this file, actually. The debugger helps you do that a lot easier because there's a graphical user interface, but you can actually follow it just by looking through this file. So we went from line 2 to line 3, and when we executed line 2, which one was this? Oh, we're looking at the while loop right now. So when we execute line 2, we should have created a variable called count and put the value 1 in there, right? Which is exactly what happened. We in the next snapshot, inside the stack frame, in the variables section, we now have a count entry and whose value is 1. But the next step after that, this is very small. Why is this very small? Well, let's look at this line. This line is the top of a while loop statement, and it actually doesn't make any modification to the state of the program. So if we take a snapshot at this line, then the stack frame should be identical to the stack frame in the previous step, which is why we don't the file doesn't recreate this part. It merely makes a reference to the previous version of the stack, so there's no need to redo this, restate this stack frame. And the same thing happened with the next line as well, because the next line was a print statement which didn't modify the state. There's something about side effects that I am planning to do, but I haven't done that yet. So I'm not gonna talk anything about side effects such as print or and perhaps network requests and stuff like that. I have not done anything to handle that yet. And so forth. And then on line 4, the variable count has been updated to 2, and you can see that that happens because we had this assignment statement to the count variable again, and so forth. So this is how this works. The time traveling debugger basically works by doing an exhaustive capture of all of the states of the entire program. And if you're watching this, I bet you might be thinking, that seems like a lot of overhead, a ton of overhead. Is this approach even viable at all? And my answer to that is I'm not sure, but I think the opportunity for like the benefit of having something like a time traveling debugger is so great that I'm willing to try. And also with this history file, and with all the previous snapshots of the program state, there are more things you can do beyond simply implementing a time traveling debugger. And such as you could answer questions about the program when you such as, like, if you're looking at a piece of source code, a function or what have you, a lot of times, like a lot of the time of a programmer's workday, I would say, is spent on trying to reconstruct how a piece of code works. A lot of times, if you're looking at code that was written by someone else, but even if you're looking at code that was written by yourself, chances are you don't remember how you put it together. Like all of that information has been forgotten, and you sort of have to reconstruct that. And if you have this history of the execution of the entire program, you can actually use it to answer questions such as, will the code ever go into this branch? Or if you had a function, say this one, you can ask and answer a question such as, like, was this function ever called with this parameter? Or how many times did the function did the program enter this line? All these questions are something you can answer, and you can have a program answer that simply by it looking through all of the snapshots within the history file. And I think that's a very, very powerful thing. In terms of how can we make this approach performant enough for real world use, that's very, very much a research question. And I'm kind of hoping that the magic of immutable data structures can allow us to solve that problem. So that's I'm gonna stop here because I feel like I've been rambling for long enough. I definitely have I definitely will give more progress updates about this in the future. So if you're interested in that, please stay tuned to this channel, or as they say, as the YouTubers like to say, hit subscribe.